Okay, now we're going to put it all together. Those three things that we reviewed are going to show up as we figure out how to analyze something called thin film interference. Instead of just talking kind of arbitrarily about it, I'm going to make up a scenario and make up actual numbers and talk you through how it works. So maybe this has happened to you before. Maybe you're at a gas station on a rainy day and there's a puddle of water on the ground. And just because it always happens at gas stations, a little bit of gas is spilled on the ground. And because of its chemistry density, the gasoline is floating on top of the puddle. So the gasoline is forming a thin film on top of the water of the puddle. Bad luck, you're standing right in the puddle and you're looking straight down at it. And as you look straight down at it, you see a nice bright reflection of orange. If I tell you that the index of refraction of water is 133 and the index of refraction of gasoline is 1.4, with thin film interference, we can figure out how thick that layer of gas has to be so that you see that bright reflection of orange. So this is how a question will be worded. I can't even really make them any harder. We'll talk through this one, and then there's some examples that we'll go through again so you can try them on your own. But this right here, this one here is thin films, and we'll just do the same scenario, the same sort of algorithm to solve it over and over again. For this first one, though, we'll go nice and slow, and I'll talk you through it. As always in physics, when you get a problem, you should sketch it. The difference between experts and novices at any topic is experts can visualize it a little bit differently. So that means for us, we got to start drawing sketches as we work to switching from being a novice at something to being an expert at something. We're going to keep things really simple, and we're going to assume that things are very rectangular. So we've got a puddle, that's a rectangle, and we've got a thin layer of gas on top. The thin layer of gas is also a rectangle. In the question, it told us that the index of the water was 1.33, so I'm going to label that. The gasoline has an index of 1.4, and it doesn't say it, but from here on out, air has always got an index of 1. I don't care really how thick the water is. The question's all about the thickness of the gas film, so I'm going to call that a thickness of letter T, and that's what we're trying to solve for. What thin films interference is about is two particular bundles of light. I'm drawing them in this diagram on an angle so that we can see them better. But the way we're going to solve it, I'm drawing it on an angle, but the light rays are actually traveling straight down. I'm just drawing it on an angle so we can see it better. And if it was on an angle, then we'd have to do that grade 10 optics Snell's law, and we could do it, it just adds a whole bunch of wrinkles. In thin film interference, there are two very, very important bundles of light. So of all the light that's coming down, so maybe it's a sunny day even though it's raining, out of all the light that comes down and hits this film of gasoline, some of the light, when it hits the gasoline, reflects off the gasoline and bounces back upward and eventually hits you in the eyeball. I'm going to call that bundle of light number 1. Bundle of light number 1 is the one that bounced off the top of the film. Bundle of light number 2, when it got to, so it came down just like the other bundle, when it got to the gas layer, it actually punched through and went into the gas. Geez, jumping a little bit. So bundle of light number 2 came in through there, but then when it got to the water, it reflected off the water and again came up and hit you in the eyeball. As far as interference is concerned, those are the two most important bundles of light. The one that went off the top of the gas and the one that went off the bottom of the gas or the top of the next layer. So top of the film and bottom of the film. There's other bundles of light, like some light when it gets to the gasoline and goes through, then it gets to the water and it goes through again. Then it gets to the ground underneath, and when it gets to the ground, it bounces off the ground, shoots back up through all this stuff, and hits you in the eyeball. If we cared about that one, we could call that bundle of light number 3. That's why you can see the ground underneath the puddle, because light's bouncing off the ground and making it to your eyeball. But for our interference, thin film interference, we don't care about that bundle. The two most important bundles are bundle of light number 1 and bundle of light number 2. There's another bundle of light that kind of ping-pongs. Oops, bring back my drawing tool. There's another bundle of light that kind of ping-pongs. So when it gets to here, it goes back down and then it goes back up. That's another bundle of light, but again, it doesn't factor into thin film interference. For thin film interference, we're just going to worry about these two that I've drawn, whatever the situation is, the one that bounced off the top of the film and the one that bounced off the bottom of the film. The next step in how to solve this is to compare them. Bundle of light number 1 was in air, and it reflected off the gasoline. So it was in an index of n equals 1, and it bounced off of n equals 1.4. That means it reflected off a material with a larger index. Bundle of light number 2, it punched through and entered the gasoline. Since it entered the gasoline has a different index. That means its wavelength, what we talked about before, different material, different wavelength. Its wavelength will be a little bit shorter. We'll deal with that later. It traveled down through the thickness of the gasoline, and then it reflected off the water. It was in gasoline, which has an index of 1.4, and it reflected off of water, which has an index of 1.33. So it reflected off an index with a material with a smaller index. So far, bundle of light number 1, it's the easier one to look at. It just reflected, and in this question, happened to reflect off a larger index. Bundle of light number 2, though, its wavelength shrunk as it went down a distance of t, and then it reflected off something with a smaller index. So just based on reflections, bundle of light number 1 reflected off a larger n, and bundle of light number 2 reflected off a smaller n. I'm going to talk about that again later in the chart, but just sort of file that away. And bad page break, but we're not done with bundle of light number 2. Bundle of light number 2 then continued, and it traveled through the gasoline again, so another distance of t. Remember, I'm drawing it on an angle just to see it, but that bundle of light number 2 went straight down t and then straight up t. So altogether, bundle of light number 2 has gone extra distance in the amount of 2t, a t on the way down and a t on the way up. Okay, continuing our analysis. If we look at just the reflection, so that stuff I wrote down just a second ago, bundle of light number 1 reflected off a medium with a larger n. Bundle of light number 2 reflected off a medium with a smaller n. What we talked about, reflecting back on the Slinky lab, reflecting off a larger n, that's kind of like hitting a fixed end. Reflecting off a smaller end, that's kind of like hitting a loose end. Bottom line is they did different things. Since they did different things, they're going to be out of phase if we just thought about the reflections. So far, based this question with these ends in the order that in the order that they are, if we consider just the reflections, the two bundles are out of phase with each other. The other thing that 2 did differently is it entered a new material with a different index. So that means its wavelength is going to change. From what we talked about before, the new wavelength is the air wavelength, divided by the n. So in this case, orange light, I made up 560. I was trying to make the numbers easier. When that orange light entered the gasoline, its wavelength actually shrunk to 400. And the other difference that we pointed out is a bundle of light number 2 traveled a t on the way down and a t on the way up, so it traveled farther by 2t. All right, if you scroll back to the question or think back, the question specifically used the word bright reflection of 560. Bright is going to be a keyword that means constructive interference. So we saw the question said a bright reflection of 560. That means that it's constructive interference of 560. That means that these two important bundles, bundle number 1 and bundle number 2, must be in phase. That's what constructive interference means. But because they reflected off different materials, different ends, one reflected off a larger, the other reflected off a smaller, they're kind of out of phase. The reflections are putting them out of phase, but also number 2 traveled a little bit farther. So as the question said that it's a bright reflection. The question requires them to be in phase, but if we just look at the reflecting puts them out of phase. So that extra distance that number 2 traveled must be the right amount of distance that it puts them back in phase. They're out of phase because of the reflecting. We need to put them back in phase because of the extra distance. To change the phase of something, remember interference is all about half lambdas. If the extra distance is exactly half a wavelength, that's going to put them back in phase. They're out of phase now, but a half a wavelength of extra distance will kick them back into phase. The extra distance has to be half a wavelength, but half of the new wavelength. So they're out of phase because of the reflecting. The question says they're in phase. That's why we're seeing bright. The extra distance must be the right length to put them back in phase. To put them back in phase when things are out of phase requires a distance of half a wavelength, but we're going to use the special wavelength in the gas because that's where the extra distance was. It traveled through the gas. Now we can kind of finish it off. The 2t, the extra distance, must be half a wavelength, or if we flip that 2 in front of the 2t to the other side, the thickness must be a quarter of the wavelength. I cooked up nice numbers. The wavelength was 400, so the thickness must be a quarter of 400, which is 100. So our answer is 100 nanometers thick. Let's scroll back up to see the question. If on a rainy day you're standing in a puddle with those indexes, air is 1, gasoline I made up 1.4, and water is 1.33. If you're seeing a bright reflection of 560 nanometer light, the only way that can happen is if the thickness of that gas is 100 nanometers, which ends up being a quarter of 560 over 1.4. That's a little bit, maybe the first one's a little bit overwhelming. Once you roll through these, here I'm going to show you, I've got it typed up next. There's an algorithm you can follow that will always work. So I'm always going to get you to sketch it. And what I would say is right up front, find the lambda prime. The lambda prime is the lambda in air divided by the index of the film. So this, when I say lambda prime equals lambda over n, this is going to be the film's n. Then look at those two important bundles of light, bundle of light number 1 and number 2. Look at those. Are they in phase or out of phase as a result of just the reflection? And here I can even give you a trick for that. I'm going to zoom over here. So for this step, the question we just did, we had a film and then we had the water underneath. The ends, I would describe those ends as out of order. It went from smallest to largest, what is the film, and then the medium was behind it. Since they're out of order, smallest to largest to mediums, in a situation like that, the reflections are out of phase. But if it was a different question, and there'll be one in the examples, let's say we've got air and then a film and then the material underneath. Air is always going to be the smallest because it's 1. If I cook up a question so that the ends go smallest to medium to largest, bundle of light number 1 would be in the air. It would bounce off the medium index of refraction, so it's bouncing off a larger index. Bundle of light number 2 is in the film, in the medium, and bouncing off the larger index. So it's also bouncing off a larger n. If your n's are in order like this, smallest to medium to largest or to greatest, then your reflections are in phase. You don't even have to remember that a larger index is like hitting a larger index, reflecting off a larger index is like bouncing off a fixed end, and a smaller index is like a free end. You don't even have to remember that fact. You just have to be able to compare, did it bounce off a larger index or a smaller index? If the indexes are kind of out of whack, small, large, medium, then the reflections are out of phase. And if they're in order, smallest to medium to largest, then the reflections are in phase. So by looking at the ends, you can tell if the reflections are in phase or out of phase. The last step in our algorithm, I'm calling it a logic step. Are the light rays the way the question asked for? So after you look at the reflecting stuff, are the light rays the way the question asked for? In the example we just did, the light rays were out of phase, but the question was talking about bright, so it needed them in phase. Since the questions were out of phase and the question wanted them in phase when we did our example, the answer to this was no, they weren't the way the question wanted. They were out of phase, the question wanted them in phase. So the answer to our little logic question is no. That means that the extra distance, which is always 2t, must be half a wavelength. If we go back to that example we did, if I switched it around and said, kept the ends exactly the same, but I said orange light was completely canceled out. If I had said orange light was canceled out, then if I don't change the ends, they're still out of phase because of the reflecting. But if I say canceled out means destructive interference. So they're out of phase, and if the question says canceled out, we want to keep them out of phase, then the answer to my logic question is yes. Then the extra distance, the 2t, must be a full wavelength because they're out of phase and we want to keep them out of phase. So there's kind of 4 different scenarios. Maybe the light waves are out of phase. Then look at the question. Does the question want you to keep them out of phase? Or does the question want you to put them back in phase? Or maybe we'll do one like this. There'll be one in the examples where the ends are in order. So maybe because of reflecting, they're in phase. If the question wants that to keep in phase, maybe the question says bright, so they're in phase of reflecting, and the question asks for bright, then the answer is yes, and the extra distance would be a full wavelength. Or maybe the ends are in order, so they're in phase after reflecting, but the question wants us to cancel out a light, then the answer to our logic question is no, and the extra distance is half a lambda. That's been a lot of talking, so I think I'm going to stop there, but we've got 4 examples for you to try. Sorry, 3 examples for you to try. We've already done one. A worksheet with just thin film questions, and then one check-in related to this. So take your time, go through the examples. I kind of think that once you try the examples, it'll click this algorithm, look at the ends, calculate the lambda prime. Are they the way the question asked for? Once you've done it a couple times or watched me do it a couple times, I think it'll click. But as always, if you disagree and it's not clicking for you, just shoot me an email and we'll figure it out.